Hello, Jeff Disher here again. Today I'm going to be talking about compilers, which is sort of leading from some of the talks I did before on programming languages. This is sort of what brings that together into how it actually matters and in what computer programmers actually do. So you might hear this term when they're talking or looking into things. So first of all, well, what is a compiler? I'm going to go through sort of what this is and what you do with it and what the benefits are. Also then the parts of a compiler. This is going to be from issues of lexical analysis, because this is for reading programming languages, syntactic analysis of the language, and code generation, so actually creating the output of interpreting a programming language and building a program. So I'm also going to go into some high-level discussion of optimization, because that's a common issue and it's one that people usually find quite interesting even when they're just coming into the area. And at the very end, just some basic references to some tools you'd use if you were trying to build a compiler yourself. So first of all, okay, what is a compiler? Well, really, when it comes down to it, it's just a program which transforms another program into a different representation. Now, usually this is going to be converting like a high-level language like C into machine code, like x86 binary or something like that. So that's how you actually take a programming language and turn it into a program. So the other things that are useful about this is it can often identify some errors for you. Things like, because the compiler can see all this code, it knows what the components do. It can say things like, okay, this thing you're trying to operate on doesn't exist. Maybe you misspelled it. This is the wrong way of using this kind of component or function. It wants you to pass in a name and you gave it a number, something like that. It can often do a lot, which really saves a lot of time when you look at things like testing and debugging, especially if you're looking at a problem in deployment. If the compiler could have told you up front, this is going to save you weeks of time. It's amazing. And also, one of the big areas, especially more recently, is, and increasingly over time, is it can also optimize the program. Sometimes the compiler can actually determine that you're doing something which, while it makes sense to a human or for someone trying to read and understand what the program's doing, it's actually an inefficient way of doing it for a CPU or for your interpreter or something like that. So it can often optimize the program for you. Similarly, it can know more things about the CPU than you should be knowing as a developer, because you want to be writing portable code, but the compiler wants to be writing fast code. So it gets over that kind of disagreement between those two. So looking at the parts of a compiler, really the way to think about this is it's a pipeline. There's sort of different components, and each one's always going to be pulling data from the component before it. And they're each giving increasingly high level or increasingly optimal pieces of information than the one beforehand. So you're looking at the first component is usually going to be your Lexer, which is the component which provides what's called the Lexer. It provides the lexical analysis of the input program. So you give it the bytes of the language, the text file itself. And it's going to create tokens. Now this is essentially just the words of the language. And the next component is the parser. Now this is actually what's going to be applying the syntactic analysis. And what that means is it's going to be applying the grammar of a language to those words or tokens that the Lexer gave it. So it converts tokens into a logical representation called a parse tree. Then there's going to be an optimizer, usually somewhere around here, which is going to be taking that logic and performing some permutations to it to come up with better logic. Basically just kind of optimal for some definition of optimal. It might be smaller, it might be faster, it might do certain things better, things like that. And the very last component that you're going to have in any compiler is the code generator. So this takes the logic and writes it back out into some form of bytes, the file. And that could be maybe the same language that you gave it to start out with. Maybe it's just optimizing what you gave it, or which is common in something like JavaScript. Or maybe it's going to be the binary, like an actual executable binary file, like if you're compiling a C program or something like that. So looking at lexical analysis, this is going to be converting the language, just whatever it's reading, the text file or something, it converts it into tokens. Now tokens are really just the words of a programming language, because some words are going to have certain meanings. They're going to be things like keywords or constants or other kinds of things, which are effectively just punctuation in a computer programming sort of sense. But these ideas show up in even English as well. It's just that the words in English are a bit more broad, but they still have the notion of there's certain things which are words, there's certain things which are names, there's certain things which are punctuation. And these things, they matter when you're trying to interpret what's going on. Now in computer languages, they're a lot easier though. And the main benefit of this when you're trying to build a compiler is you don't have to think about what the text itself looks like when you're building the next components, because those get more complicated. So just looking at a quick Lexer example, like if I were to use this English sentence, well, okay, my name is Jeff. Well, how is that carved up into tokens? Well, in English, this is very simple. There's words, which are just combinations of letters. There's spaces, which are just going to be spaces, tabs, new lines, things like that. And they don't really matter in the language. They just separate words. And then there's going to be punctuation, things like the period. So here you end up with this kind of sequence of tokens coming out that would come from a Lexer reading this sentence, applying kind of an English word structure to it. And the same thing happens in programming languages. So syntactic analysis is the next phase, and this is where you get your parser. So it takes those tokens created by the Lexer, the words, and it builds them into a parse tree. Now this is basically comes down to, the parse tree is a description of the grammar of the language. So if the Lexer is giving you the words, the parser is going to be putting those into kind of structural idioms or something. Applying the language, things like this is the subject and object, this is a verb, stuff like that. The same concept exists in English, it's just much harder to do because the languages, human languages are richer. So what you'd often see in a real compiler implementation is something which is yet another phase, which is going to change, doing something what's called semantic analysis, which is when it's going to change a parse tree created by a parser into something called an abstract syntax tree. And this is really just kind of the high-level description of the logic itself. And it has less of the nuances of a specific language. There's still going to be some, but generally speaking, and ideally, it has very few. I'm not going to go into detail on that, though, because it's kind of repetitive because it works similarly to the parser and is more language specific. So looking at a parser example then, using that same sentence I had, assuming that we were running that Lexer that I mentioned before, you'd end up with a parse tree that was something like this, where it would know that my applies to name, so that's kind of a node in the tree. It's kind of a logical idiom. And the rest of this sentence goes together this way with other kinds of verbs that are important, punctuation's important, things like that. So it can put all this together and have sort of a description of the logic of the sentence. Looking at code generation, which is going to be the last phase of an actual compiler implementation, now what this does is it converts the logical structure back into a linear language. Remember that a program is essentially, it's like the difference between a thought and your words. The logical structure and the linear language, it's the same thing. It's that when you're thinking about an idea, it's not language. You try and explain it in a language so someone else can interpret what you were trying to say. This is the same way a computer works. There's sort of the logic of a program, what it's actually trying to do, and you're trying to describe that in a linear language, either for a CPU or for an interpreter, something like that. So it can read it back and try and understand what you were getting at. And of course, this means that this is typically going to be the language used by whatever your target environment is. There's reasons why it might be something else, but generally it's going to be either the binary for your CPU or the language used by your interpreter, like a Java bytecode or JavaScript minified script. And this is also where you get things like micro-optimizations being applied. These are kind of specific to the CPU and potentially even the version of the CPU it is. This is things like instruction scheduling, which is the idea that sometimes in a CPU, running certain operations in a different order will be faster but give the same result. And this is something that's not worth, as a human, you knowing about, because they vary wildly from one CPU to another, but it's something that the compiler does know about. That's its domain. You're also going to have things like machine state tracking, which basically means it's going to know about, okay, well, how many things are currently in flight? Like, how many pieces of information do I need to keep track of? And, okay, well, which ones am I operating on most? Let's put those where I can get to them really quickly. That kind of optimization is also something in the code generator. But when you look more broadly at optimization, really what it comes down to is there's multiple ways to say one thing. And sometimes when you look at it from the position of like an English example, you might want to optimize a sentence which is otherwise overly wordy. It's got redundant components to it. There's some weird non sequitur in the middle of that description, or it's generally too complex for your target environment. for example, you want to think about an optimization problem, which comes up with the English language, is say you're trying to describe something you were doing at work to some of your colleagues. You're going to use a very technical, very specific way of describing it that assumes a lot about them. It assumes that they have a lot of your same background, that they've worked with you before, so they understand your nuances and idioms and speech. So you can have a very, very effective high-level conversation that's very, very tightly coupled to the kind of interaction you have. It's highly optimal, but only for that environment. If you were to do, for example, the same thing when talking to a bunch of, say, elementary school students to try and explain to them what you do during the day, well, you're not going to explain it the same way because they're not going to have any idea what you're talking about because they haven't gone to school for the same things you have yet. They're young, they have a different world they live in. So you're going to optimize it for a different environment. You're going to use simpler words, simpler ways of explaining it, and keep the description kind of further away from the details. And this is really what a compiler does as well. It's optimizations for a specific environment. So the optimization concept can apply either semantically, like what I was saying before, which comes sort of somewhere after the time you parse it and before you do the code generation, that kind of high-level optimization based just around the ideas, or it's going to be very machine-specific, and this is the optimization that's going to come up in the code generator. So when you're looking at building a compiler, if you were to do it yourself, or if you're just curious and want to look into what the next components are, or do a deeper dive into some of what I'm talking about here, there's a few things. You're going to have a bunch of tools that help you out. First of all, there's Flex, which is based on another one called Lex. Either of those work fairly similarly. And this is a Lexer generator, which is great because writing a Lexer is very, very tedious and error-prone. So what you can do is actually give this program a description of, okay, here's what the words of my language look like. And it'll generate a C program for you, which actually can understand that language and generate tokens for those words. So this is great because otherwise that's a lot of work. There's another tool called Bison, which is based on another one called Yak, an older program. And this is a parser generator. So it's something where you describe for it, okay, here's the grammar of my language. Here's what the language would look like logically. And it's going to generate for you a compiler or a parser that can change the tokens generated from the Lexer into a parse tree described by your grammar, which is great. Also, it can generate a description of what that parser would be instead of the parser itself, which is good if you're not writing a compiler in C. So this saves you a lot of time, massive amounts of time, because these are both big components, but they're very repetitive. So it's good that there's tools that build them for you. And also, just to point out how many tools like this have existed at various points in time, the name Yak was actually an acronym. It stood for Yet Another Compiler. So that just gives you some perspective on how many of these tools have been written over time. But Flex and Bison these days seem to be the common ones. And another one, which is a more recent idea, kind of within the past, I think it was since about 2000, more recently than that even, is a tool called LLVM, which is it's sort of the intermediate component of some modern compilers, because no matter what you're reading, what language you're reading into, and what language you're writing out to, in the middle you're going to have this idea that there's an intermediate form of the logic itself, of the program. And so you need something that can operate on that, can standardize how it's specified and what you can do with it, and can also perform standard optimizations on it, or common optimizations rather. So LLVM is something which is showing up in a lot of tools as time goes forward because it's easy to interoperate in that way, and it gives you a lot of what you'd otherwise need in a real compiler. So it's a useful tool. So I hope that was interesting and informative. Again, post a comment here if there's any questions, or get in touch with me. And if you have any suggestions for a future talk, then yeah, don't hesitate to contact me. I'm always interested in hearing what people have to say and what they want to hear because I like talking about this stuff. Anyway, thanks a lot, and subscribe if you're interested in continuing videos. Thanks.